Good afternoon to everybody, and let me start off with my presentation today. I'm actually going to talk about my PowerAmerica project, which is the Integrated Intelligent Gate Driver and Interface System for MV applications. So I'll focus this presentation on the gate driver and its applications for our medium voltage converter systems for silicon carbide based high voltage devices. So we'll talk about the design, qualification, and the intelligent gate driver and some of the tasks that we are doing. So as we all know, the PowerAmerica and funding from DOE and earlier from ARPA-E has actually spurred the development of high voltage silicon carbide devices, and also funding earlier from the DOD, particularly ONR, has actually helped to develop these devices, which have made a significant impact on the medium voltage power conversion systems that are now possible. So here are examples of the highest voltage devices that have been used in converter circuits, particularly silicon carbide 15 kV IGBT and correspondingly 15 kV MOSFETs. So this is if you look at the left picture here, and if you can see my mouse, then this is the IGBT die, which is a 15 kV 20 amp die, 8.1 millimeter by 8.1 millimeter, and these are the two JBS diodes, which are 8 to 10 kV blocking and therefore connected in series for this 15 kV co-pack. Similarly, for the MOSFET, again, we have two dies which are connected in parallel. So, and again, the two JBS diodes connected in series. The same kind of a structure in a closed module for a 10 kV silicon carbide MOSFET with base plate isolation is shown out here. So with new development going on in terms of packaging, particularly achieving a base plate isolation of 25 kV has been qualified by API and Wolfspeed into this kind of a package now, which again is a half bridge, which is possible to make it into a half bridge. Here it is packaged as a co-pack, which means a 10 kV MOSFET and a 10 kV JBS diode connected in anti-parallel. The important thing about this package, as I said, it's qualified up to 25 kV base plate isolation, and again, the gate connection is actually provided with a different kind of an interface, which is an RF interface. So let me jump into the gate driver design and qualification. So our motivation is to drive these devices that we are talking about at medium voltage. We need a gate driver, and the most important thing of the gate driver is to achieve a very high isolation voltage. So the challenge actually is making a gate driver that can withstand 10 to 15 kV isolation while it is switching at 10 to 20 kilohertz, and with the high dB by DTs that are required from these silicon carbide devices to achieve low loss. So the question is that how do we actually make a gate driver which has this kind of isolation and of course can switch at medium voltages all the way up to a DC bus voltage of something like 11 to 12 kV and at 20 kilohertz, and offer all the things that we need from gate drivers. So DSAT protection, current sense, and of course, fast protection in terms of turn off, in terms of faults. So immunity to noise, gate voltage regulation, and the high isolation with the minimum parasitic coupling capacitance that we can achieve. So these are some of the challenges which actually makes this project very important and interesting, such that we can use these high voltage devices. The problem so far has been that with silicon devices, we have always been limited to 6.5 kV, and therefore the commercial gate drivers that are available are actually available up to this 6.5 kV, and they are qualified not for very high voltage isolations or the isolations of 10 to 15 kV. Most of these things are qualified up to around 6 to 8 kV isolation. And they do not withstand very high dB by DTs, because that's not what is required for silicon IGBTs at particularly these high voltage voltages. So commercially, as I said, concept gate drivers are available, and here is a commercial spec of a gate driver, and you can see that these gate drivers will produce 15 volts minus 10 volts. Switching frequencies can go up to 10 kV, and typically for 4.5 or 3.3 kV, and dV by dt capabilities touching 50 kV per microsecond, but the isolation capacitance is around of the order of 8 picofarads. The VC SAT monitoring voltage is also pretty high, 10.2 kV, 10.2 volts for these gate drivers. What we are seeking to do here is, for silicon carbide high voltage devices, is achieve turn-on voltages which are actually higher than the 15 volts, and go all the way up to 20 volts, or maybe a little bit higher than 20 volts, and turn off, of course, minus 5 volts, and switching frequencies all the way up to 20 kilohertz, even pushing higher for silicon carbide MOSFET. And we need dV by dt capabilities which are much higher than 50 kV per microsecond, and coupling capacitances which are less than 5 picofarads, typically around 1 picofarad. So towards that, what we have done, here is a commercial picture of a commercial concept gate driver, and towards that, this is a picture of our first generation gate driver that we had done under ARPA-E project with the 15 kV silicon carbide IGBTs, and later we have used these for, of course, the 10 kV MOSFET and the 15 kV MOSFET also. In this case, this is the isolation transformer, and we have achieved 15 kV to 18 kV isolation of this transformer with 3.4 picofarad of coupling capacitance. So I want to show you what the gate driver has to do actually for these kind of high voltage devices. So here is a representative example of switching of a 15 kV silicon carbide IGBT at 11 kV DC bus voltage, and now these devices, which are punch-through devices, experience a very high dV by dt. So during the turn-on process, we have dV by dt which are 110 kV per microsecond before the punch-through, and lower dV by dt after the punch-through. And during the turn-off, we again have lower dV by dt's of the order of 16 kV per microsecond before the punch-through point, and high dV by dt's after the punch-through point. So these numbers are typical, actually, when we are driving these kind of high voltage devices. So we need to make sure that our gate drivers are capable of actually achieving these kind of dV by dTs and are capable and reliable to work under these kind of dV by dTs. So a typical gate driver power supply design actually goes along this way. We have a DC power supply, a DC source, and a H bridge with a coupling transformer, and then a linear regulator giving us 20 volts and minus 5 volts. So as I said, the challenge is actually in the isolation transformer, and so we have actually gone through a whole host of different designs, as you see, for the transformer, and we have characterized magnetizing inductances and the coupling capacitances at one single point, which is, in this case, what we are reporting is a 50 megahertz. For the capacitance, magnetizing inductance at 50 kilohertz. Okay. So as I actually mentioned, we can achieve this particular design using capacitances which are of the order of 0.5 or 0.6 picofarad, and typically the range of 1 to 1.5 picofarad.
Can you stop for just 1 minute, please? Can I ask everyone to please mute your end if you're not speaking? I'm trying to mute people as they join the meeting, but please mute your phone to reduce the background noise. Thank you.
Okay, so here's an example where we have tested a particular isolation transformer design where we have achieved around 1.4 picofarads, and every time I say this, this is all qualified up to at least 15 kV of isolation. So this number, why are we talking about this number? This number is important because if we have this kind of dV by dTs, then we can quickly calculate that with the coupling capacitance, the C dV by dt is the coupling current that is going to actually be flowing into the gate driver circuit because of the switching. So every time we have these kind of high dV by dTs, we will have these coupling currents that are going to be actually flowing and disturbing the gate driver power supply. So that is the reason why we want to actually bring this down to very low numbers, such that our coupling currents are reduced and the immunity of the gate driver is, or the power supply of the gate driver is actually increased, which leads to the reliability part of it. The gate driver itself is obviously going to be fiber optically or triggered, and so that's what is shown out here from the electronics point of view. And as I said, the major challenge is the isolation part of it. So once we actually have a gate driver that achieves these specs that we laid out in the earlier slide, the important aspect is to qualify this gate driver. And this qualification of the gate driver should follow a few different steps. So, of course, as we do in all our low voltage power electronics, we verify the functionality of the gate driver by making sure that we are getting these pulses, which is both at 20 volts on and minus 5 volts off. So that's just the first test. Then we want to actually take these gate drivers and build double pulse test setups where we are pulsing the device under test, because we want to characterize the switching losses of these devices under different VDC as well as different currents that we can actually will build up in the inductor and different temperatures. So we can actually put these on a hot plate to measure or to force the junction temperature to go higher. So this is typically what we do, and we do this because, as I said, we're doing this because we want to characterize the losses or the switching losses of the device itself. But we want to turn this around and ask the question that, okay, this is the first step for actually testing our gate driver itself. But then that's not enough because this is just a pulsed operation. So the next step is we then take these gate drivers and we actually go into a boost circuit where we run these things under continuous operation. So at the switching frequency which the gate driver has to work. So which is, as we said, targeting for these high voltage devices up to 20 kilohertz at least. And so that gives us the functionality of the gate driver under high switching frequency, but doesn't really test the gate driver for high side operation. So to do that, again, then we actually take the gate driver and we put it into a buck circuit after that to test the high side operation. And we can actually do this circuit of the boost and the buck following. So this is one of the ways that we actually want to test the continuous operation and validation of the gate driver. After we do this, actually there is one more step or two more steps that we do. One is that we then go into a buck boost circuit where we swing the voltage on the gate driver itself from positive to negative. And that is a very important test also. And then the last test is that we build a half bridge pole and we actually operate that pole with the high side driver and the low side driver under continuous operation with the switches. So here's a couple of examples, and I'm going to talk about the 10 kV MOSFET for most of the presentation out here. So therefore, testing all these at 6 kV DC bus, and our devices are typically 10 amps. So now you see, turn-off transitions with a gate resistance of 10 ohms and turning off the device. So this is the VDS with a single slope for the MOSFET, the current turn-off, and the gate driver VGS operation. Similarly, turn-on of the gate driver for the MOSFET, we do have a turn-on current, so EON gets affected by this, and the VDS, again, a clean single slope due to the MOSFET characteristics and the gate driver VGS operation. So as I said, we definitely need to make sure that we have a continuous operation of the gate driver with a boost switch. Again, it's for mainly continuous operation, not testing the gate driver for the high side because this is a low side switch. So then we actually follow it up with a boost and a buck converter where we are now testing gate drivers for both high side as well as the low side. And we can change our operating points and test the gate drivers for different duty cycles. So these are some of the steps, and then I'm not presenting out here, but if one is interested, one can definitely look at some of the papers that we have, or please contact me and I can provide you with more details about testing with buck boost as well as the pole or the half bridge pole test that I mentioned. So I want to jump into the intelligent gate driver function and the qualification of these gate drivers. So to take advantage of the silicon carbide devices, we may want to actually change the dV by dt, and also we want to build in some smarts into the gate driver. So we are showing an overview of our first thinking process of actually going towards an intelligent gate driver, where we want to measure a few things which have to come out of the gate driver. Of course, we want the status fault, some kind of idea of the temperature, the VDS, the VGS, ID, and IG. So as a first step, we have included and validated CPLD into the gate driver itself, and this itself is a major step because the gate driver, as we all know, operates in a very high noise environment. To make sure, and therefore we have to really make sure that a CPLD logic device is going to work reliably and be immune to these noise environments. And then, of course, we want to convert all these signals that are being interfaced with the gate driver itself into optical, such that we can transmit it to another interface board, as we call it, where we can do further processing. And there, of course, we can actually use a FPGA-based system and do all kinds of processing. This is away from our high noise environment. But the most important thing is to actually make sure that we have reliable operation of this intelligent gate driver itself. So here's a picture of what we have achieved as part of our PowerAmerica project, where this is the gate driver, this is the intelligent gate driver, and where we have a CPLD logic, we have the optical transmitters, receivers, and we have included an active gating function in our gate driver. And of course, we are showing you the switch for where the gate driver is connected to. So again, this is the complete gate driver circuit, the sensors, all the drivers are there. The DSAT sense itself is actually a 8 kV silicon carbide JBS diode, and so this is required instead of actually stringing together a lot of series silicon diodes. So these are the different things that one has to do to go towards this kind of a intelligent gate driver. Here we are showing you some one particular aspect of the active gate driving, where we can change actively the resistance, the RG of the gate driver itself by the CPLD logic. So we can control these RGs at different points, and we can time these as a function of either time or as a function of current and temperature and those kind of things. As I said, we do have a JBS diode, which is itself a silicon carbide JBS diode for the VDS sense part of it. So this is showing the functionality of the active gate driver, and you can see now that we can actually actively change the gate resistance, and we can now affect the current and change the dU by dt with for the MOSFET. So now we have brought down the dU by dt or the VDS to very low values of 1 kV per division in this case, and so this is showing actually the functionality of how an active gate driver would work, and of course the tuning can be done based on the application, the device, the operating point, and so on. So we can actually change our RGs from as high as 50 all the way up down to 4.7 ohms. So again, this is showing the validation of the circuit or the gate driver itself. So the IMGD or the intelligent gate driver, and we have the boost circuit, the boost buck circuit, where we're driving it with the generation, our earlier generation gate driver, and validating what we just said. So continuous operation, both the high side as well as the low side switch with different duty cycles, as I mentioned earlier. And in this case, the input voltage is 1.25 kV, the output is 5 kV. And so the next aspect is that, as I mentioned earlier, that we can take, once we do an intelligent gate driver, we can now take these signals that are coming from the intelligent gate driver into another interface board, which is optically connected to these gate drivers. So the board that I'm showing out here can interface with 12 such gate drivers, and on this board we have a FPGA. So now one can actually start making central decisions of a converter system based on inputs from all these gate drivers. Here is an example of how this sensing works. So for example, what we are showing out here is a continuous operation for a boost buck circuit at 5 kV, and the gate driver is now sensing and recreating the VDS, and as you see out here, and relaying this back. So it's actually getting this on the gate driver board and then relaying it back to the interface board itself. So based on this, now we can start taking some central or some decisions on the VDS, and we can continuously monitor this VDS to see if there is dynamic changes in the RDS on and so on. We also can sense temperature, and here's an example of sensing of the temperature. The temperature sense has a lot of noise, as you can see there in the peaks. Again, this is through the gate driver optically transmitted into the interface board. But for the temperature sense, we do know about these noise issues, and for right now, we do know where to measure. So actually, we can create windows to make sure that our measurements are consistent with our reasonable values. And to do this, and the reason I say this with confidence is because so this is the measured value that is coming from the gate driver and into the interface board. And we do have thermal cameras where we can actually measure the base plate of the device itself. And because we do know the packaging details of the device, from this base plate we can calculate temperatures, we can calculate the junctions, and we can correlate this with our results coming out from here. And that's the reason I say that these things are pretty close, actually. So you can see these numbers here being pretty close to what we are estimating from our gate driver itself. So again, I'm showing validation of the IMGD in our boost circuit, VDS sense through optical fibers. And this is opening up now this whole area of actually diagnostics as well as prognostics of the devices sitting at the gate driver itself. So some more results of the validation of the gate driver, the boost circuit, and then the boost buck circuit. And the switching frequency for these 10 kV, 10 amp MOSFET is 10 kilohertz. Now, this question always comes up, is that, what is the short circuit capability of these devices in the first place? And if a short circuit happens, how good is our gate driver to sense it and to do something about it? So we thought we should test this out. So we have our intelligent gate driver, and we have a 10 kV, 10 amp device, MOSFET. And what we are showing you here is that this MOSFET was operating, so we intentionally caused a short on the device with 3 kV on the DC bus, and the device or the die so there is a single die here. The die which is supposed to carry 10 amps actually went all the way up to 150 amps. And the gate driver was able to detect and turn off the device in 2.5 microseconds. So this is something significant, and this gives us a lot of confidence about the short circuit capability of these devices. So now one is going to ask the question, well, these devices are for 10 kV, and so with a 6 kV DC bus, you should really test it at 6 kV DC bus. Yes, we are going towards that as our next step, but this is a powerful first step where we are showing that with 3 kV on the DC bus, this die does not even fail, or this device does not even fail when we have 150 amps in the die, and the gate driver is able to detect and shut it off in 2.5 microseconds. So we think a significant step in terms of building confidence for the short circuit capability of these devices, the gate driver capability, such that we can actually go towards medium voltage power converters. So most of these things I've said, so I'm going to quickly skip in the interest of time here. I want to show you that we took 6 of these 10 kV MOSFETs, and these are our earlier generation MOSFETs, and we built a simple 2-level 3-phase converter. And we have a boost converter which actually is built up with our 15 kV IGBTs. That gives us a 10 kV DC bus, but in this case we went up to 6 kV DC bus, and we wanted to operate this as a 3-phase 2-level converter, and we also wanted to test out that what is the switching frequency we can go up to. So starting from 10 kilohertz, and what else can we do with these devices? So here is something interesting that we can do with these devices, and now, remember, I'm not showing you the photograph of the system because of my slide limitations, but each of these devices has our gate driver. And so now, starting off at 6 kV DC bus with a modulation index such that we get 3 kV on the AC output voltage, 5 kilowatts and 10 kilohertz switching frequency to reproduce a fundamental frequency of 60 hertz. So clean waveforms of the current and the 3-phase currents and the voltages. So our idea is to push up this fundamental and to ask the question what can be done with these devices. So we went to a fundamental of 240 hertz. We came down a little bit on the DC bus because our inductors are not very good, and therefore they have a lot of capacitance, and we have spikes due to these capacitances. And then going up to 400 hertz, again, 3-phase currents and voltages, and going all the way up from 400 hertz to 720 hertz and 1 kilohertz. So oops. Okay. So what I wanted to show you is that in this case, we have a 1 kilohertz fundamental, and with reduced 3 kV DC bus, 900 volts AC. Current is very small in this case, and therefore the power is 1.5 kilowatt. But my point is, and this has a switching frequency of 20 kilohertz. You can't see it because this thing is blocking it right now. But my point is that the gate drivers work at this frequency. We are able to take these MOSFETs, build a simple 2-level converter 3-phase, and we can produce a fundamental frequency which at medium voltage, which is going all the way up to 1 kilohertz. So this is something powerful that we are saying with these devices, because silicon cannot do this. Okay, so the other thing I want to quickly show you is that we actually took 2 of these devices, the 10 kV MOSFETs, and we put them in series, And so we are using the same gate driver that we have, and we are showing series connection of two of these devices. And the idea is to go up to higher DC bus voltages. So in this case, we have 12 kV DC bus voltage, 6 kV across each of these, nominally across each of these switches, and very simple small RC snubbers. And now you can see the voltage sharing of the two devices and the total voltage. So turn off of two series connected devices, MOSFETs, with the gate drivers with 12 kV across the entire DC bus voltage, 6 kV nominally shared, and perfect turn off, with no mismatch in the turn off, and of course with no matching of these devices, and very clean waveforms. So this is again very interesting because we are trying to showcase what these gate drivers can do, and we are opening up this whole new area of now series connection of these high voltage devices itself to go to even higher voltages DC bus voltage. Again, to showcase what these gate drivers can do and what these devices can do, we actually took 4 of these IGBTs that we had earlier, which is the 15 kV IGBTs, and with a 10 kV DC bus, and switching at 5 kilohertz fundamental of 5 kilohertz, and here's continuous operation at 6 kilowatt. So we have a 10 kV DC bus. Each switch is blocking 10 kV and switching under those conditions. We have a pole-to-pole output for the H bridge, which is 20 kV peak to peak, and nice sinusoidal current into RL load, and 6 kilowatt continuous running at 5 kilohertz for 15 minutes. So, I wanted to quickly wrap up and take your questions. That these are some of the future tasks that we are doing. Is we are fitting our IMGD with the XHV-6 modules from Wolfspeed, and this module is actually now laid out to be a very high current module. It can take up to 36 dies and can be arranged as a single switch or a half bridge. And so now this whole area or realm of medium voltage power converters at high power is a reality. And what we are showcasing in this project is that we can design, evaluate, validate our gate drivers under continuous operation, and then put them into converters for medium voltage operation. We can also do short circuits. We can actually protect our devices with the gate driver under short circuit conditions, and which are one of the important questions for the medium voltage operation. So that's all I wanted to present today. Would be very happy to take your questions. Thank you.
All right, thanks very much, Dr. Bhattacharya. Because there's so many folks on the line, I'd like to ask you to use the chat option in the toolbar for WebEx to submit your questions. And the first question has already been submitted. I'll read the questions out so everyone can hear them clearly, and then Subhashish will answer them. Are there any estimates of potential benefits in terms of energy losses for intelligent gate driver for medium voltage applications?
So potential, can you please repeat? Can I see the questions? I'm trying to get to.
Yeah, you should be able to see it on your screen. It says, is there any estimate of potential benefits in terms of energy losses? Oh, I'm sorry. No, you have to open up your chat window. You should be able to see them up at the top. But it's simply, is there any estimate of the potential benefits in terms of energy losses for the intelligent gate driver for medium voltage applications?
Yes. So right now, where we are in terms of validating this is we have seen or reduce the losses by around 10 to 15% from a normal gate driver with active gating. But I must mention that the loss reduction is one aspect. The reason why we are going into the medium voltage, into the intelligent gate driver is because we actually want to turn this gate driver into a diagnostics and prognostics unit, which is looking at the health of the device.
Thank you. Are there any other questions? Any more questions for Dr. Bhattacharya? I still have everyone muted, so if you want to speak, you can just unmute. If you can't find the chat window, just unmute yourself and speak your question. Okay. Can you explain the next question submitted? Can you explain in more detail how the online sense the temperature, how to sense the temperature online?
Yeah, so for these modules that we had, we do have a temperature sense in the module. There's a thermistor in the module itself. And so we're getting the feedback from there. And the important thing is that we are isolating it through a gate driver such that we can optically transmit it to the interface board. So right now there is a temperature sense, and because we do have a CPLD, we are going into actually estimating the temperature based on the model of our package itself.
Okay, thank you. The next question is, what is the reason the 2-series MOSFETs can have a balanced VDS?
Pardon me, what is the reason?
What is the reason the 2-series MOSFETs can have a balanced V sub DS?
Yeah, so we do have a small RC snubber across the MOSFETs. And so the RC snubbers dynamically balance the voltage during the turn-off process that I'm showing out there. And that's the reason why these voltages are closely matched. It is not because we are tuning the gate drivers in terms of the turn-on and turn-off times between the two gate drivers. So we are not doing that. That in my mind is something that I would want to reserve as an insurance for dynamically balancing the voltage. The voltage balancing needs to be done with a small RC snubber.
Thanks. The next question is, could you explain what probes have been used?
Yeah, very, very good question. So the differential probes for measuring high voltage are the CIC research probes. And these probes differentially go up to 20 kV. And so those are the best probes that we can currently get.
Okay, the next question is, what is the isolated gate drive power capability, and does the isolation capacitance scale directly with increased gate drive power?
Okay, so the isolated gate isolation voltage that we have tested up to is 18 kV. So our gate drives are qualified typically up to 15 kV isolation, and in the worst case we have tested up to 18 kV isolation. The coupling capacitance actually can be made constant or does not have a relationship or can be designed not to have a relationship with the gate driver power requirement. And there are geometries to actually do that. And that is the reason I showed a whole host of a table where I showed different core materials for actually building these isolation transformers. And each of these will be capable of actually going up to certain peak power requirement.
Okay, we have lots more questions. The next one is, does the gate driver voltage affect short circuit peak current?
Gate driver voltage. No, what we were testing for, typically not. What we were testing for is that if there is a short circuit, we wanted to figure out whether our gate driver is good enough to detect it and to do something about it and to shut it off. And that is what we were showing. And we showed this thing up to a 3 kV DC bus or 3 kV across the device and the device going through a short circuit.
Okay, thanks. The next question is, during operation, can the intelligent driver measure threshold voltage and VDP to avoid converter failure?
Yeah, the computation of the dV by dt can be done, and that is being done, actually. That's a number that can be transmitted back into the interface board. Can it measure the threshold voltage? That's a little bit more tricky, I think. So I don't know. We don't know the answer to that question right now. We are trying to look into it, but we don't know the answer.
Okay, the next question is, when a circuit is running, for what reason does the gate resistance need to be changed on the fly?
So the gate resistance is, the change of the gate resistance is what would control the dV by dt. So it is a mechanism of actually controlling the dV by dt. And of course, it has a loss penalty with respect to that. So the dV by dt is important not only for the gate driver, as we were talking about in this presentation, but because this converter is going to interface to an inductor at the output or to a transformer. And because of the coupling capacitances of either the inductor or the transformer, one will have coupling currents depending on the dV by dt and the coupling capacitance. And so control of the dV by dt is actually important. Also, control of the dV by dt is important to control the peak currents.
Okay, that was the last question. Are there any other questions anyone has? Any last-minute questions before we end today's webinar? Any more through the chat window or even verbally? Okay, if not, then I'd like to thank all of you for participating today. And I'd especially like to thank Dr. Subhashish Bhattacharya for a very interesting presentation. I will hopefully meet with you all again, as I said, on February 1st for our next webinar featuring Dr. Jay Balaga. And if there are no questions at all, then we'll end today's webinar. Thank you very much for joining us, and have a wonderful holiday season.
Yeah, and I just wanted to quickly mention, Rogelio, is that, you know, if people have questions or they think about questions, they can always reach me by email or phone, you know, whatever.
Okay. You can submit, if you go to the PowerAmerica, if you don't know Dr. Subhashish's contact information, you can go to PowerAmerica.org and submit the question there, and I will relay it to Dr. Bhattacharya, who can respond to you directly. All right, thanks, Subhashish. We'll see you soon.
Okay, thank you. Thank you, Radio. Thanks for everybody for participating.
Goodbye, everyone.